Each atom carries a record. Every collision, every exchange of energy, written permanently into the fabric of physics. The laws of the universe forbid the erasure of that record, not as a theory, as a fact. And one object breaks the fact completely. Black holes swallow records whole. The blow escaping carries no memory of what fell in. For 50 years, the two pillars of modern physics, quantum mechanics and general relativity, have given opposite verdicts about whether those records are gone. The stakes go deeper than physics. If a black hole can permanently erase a record, then reality does not keep a continuous history. Existence can suffer irreversible amnesia. The field tried to escape. A comfortable framework emerged, adopted by an entire generation. The framework held for 20 years. Then 4 physicists proved the framework was logically impossible, and the crisis reopened worse than before. Every remaining option required sacrificing a foundational principle that all of physics depends on. For 7 years, nobody could find a way forward. The tools that would eventually break the deadlock had already existed for over a decade. Nobody had aimed those tools at the right question. When the answer finally arrived, 2 independent groups submitted the same result on the same day, neither aware the other existed. The answer does not just settle whether the records survive. The answer may reveal that the original crisis was never about the records at all. If you enjoyed journeys that change how you see reality, hit that like button and subscribe. Nothing is ever lost. Every atom in the universe tracks where every atom has been. Every collision, every exchange of energy since the first fraction of a second after the beginning, all of those events are recorded permanently into the quantum state of the universe. The cosmos does not forget. Not once in the entire history of the universe has a single quantum record been erased, and according to the deepest mathematics that physicists have ever produced, the cosmos cannot forget. One calculation says the cosmos can not scramble the record, erase the record permanently, with no path back to what was lost and no method to reconstruct what vanished. The physicist who produced that calculation did not expect the result. The calculation was supposed to be routine, a confirmation that would barely merit a footnote. Stephen Hawking was 32 years old in 1974. Already famous for mapping the geometry of black holes, Hawking decided to apply quantum field theory carefully to the curved space near a black hole's boundary. The goal was modest. Apply the equations and see what comes out. Nothing that would challenge the foundations of physics. Hawking was working at the Department of Applied Mathematics and Theoretical Physics in Cambridge. The office was small. The calculation was not. What the equations produced after months of careful work was radiation. A glow, faint and thermal and featureless. The mathematics revealed that empty space near a black hole boundary is not truly empty. Pairs of particles flicker into existence at the edge. One falls inward, one escapes outward. The escaping particle carries energy away from a black hole. The black hole loses mass. Over timescales far longer than the current age of the cosmos, a black hole shrinks, and eventually a black hole vanishes. The object disappears. Hawking expected the glow to carry some trace of the material that had fallen inside, some fingerprint, some residue of the original structure buried in the signal. The expectation was completely wrong. The glow carries nothing. A black hole formed from a collapsing star and a black hole formed from a collapsing library produce the same radiation, identical temperature, the exact same featureless spectrum in every wavelength. Nothing. The radiation does not encode what fell inside. The radiation cannot encode what fell inside. Hawking checked the result and rechecked the result and checked again. The mathematics held every time. Colleagues at Cambridge reviewed the work and found no errors in the derivation. The calculation was airtight. Hawking published the paper in 1975, and the title gave no hint of the devastation inside. A quiet, technical title for a result that would consume theoretical physics for the next half-century. The consequence of that paper took the rest of physics years to absorb fully. If the glow carries no record, and the black hole eventually vanishes, then the record of every particle swallowed is gone. Not stored somewhere hidden, not smuggled out through some back channel, gone. For the first time in the history of physics, The equations described a mechanism for permanent erasure, deletion with no undo. To feel why that result is dangerous, to feel the threat buried inside the mathematics, consider one example. Burn a book. Watch the pages curl and blacken and crumble into ash. The ink becomes gas. Smoke scatters into the atmosphere and the book looks destroyed. But every atom that composed every page still exists somewhere. Every photon released by the flame still travels outward at the speed of light. With enough precision, with enough computing power, every word on every page could be reconstructed from the scattered remains. Fire destroys the object, but fire does not destroy the record. Information survives, always. That principle has a name: unitarity, a guarantee that quantum states evolve forward in time without ever losing track of where those states came from. One future maps to exactly one past. The math is airtight. And for the entire history of quantum mechanics, covering nearly a century of experiments, no measurement has ever found a single violation. Not one. Hawking's calculation said black holes violate that guarantee. The collision is total. The most successful theory in the history of science, quantum mechanics, says records are permanent. A calculation grounded in the other most successful theory, curved space-time, says records can be destroyed. Both theories have been verified to extraordinary precision. Both theories have never been wrong, and in the one place where both theories apply, both theories deliver opposite verdicts about whether reality keeps a permanent record. The collision cracked theoretical physics in half. On one side stood Hawking, along with a generation of relativists who trusted the geometry. Curved space-time was clear. The radiation emerging from the boundary was thermal. Records were gone. On the other side stood a smaller but fierce group. Leonard Susskind at Stanford, Gerard at Hooft in Utrecht. Both insisted the quantum law cannot break under any circumstance. Both insisted Hawking's calculation, however brilliant the calculation was, must be missing something. Neither camp could prove the other wrong. Neither camp would yield, and what followed was not a polite disagreement. Susskind called the period a war. The word was deliberate. For nearly 2 decades, the two sides collided at every major conference in theoretical physics, at Aspen, at Princeton, inside the Institute for Advanced Study, where hallway arguments between Susskind and Hawking outlasted the scheduled lectures. During a string of workshops in Santa Barbara, where debates ran past midnight into the early hours of the morning, the confrontations were direct. Susskind and Hawking occupied opposite sides of every panel, every debate, every public discussion about what a black hole does to a quantum record. The disagreements were sustained, sometimes personal. Susskind described the experience of arguing with Hawking as frustrating in a very specific way. Hawking was so certain, so calm in the certainty, that the certainty itself became a weapon. At one gathering in the late 1990s, Hawking stood before a packed auditorium and made a declaration. Information loss, Hawking argued, was not a flaw in the calculation, not a bug, a feature, a deep property of the boundary where gravity and quantum physics collide. The cosmos does not preserve records at that boundary, Hawking said. Half the audience nodded in agreement. Others sat rigid, arms crossed, refusing to accept the conclusion as anything more than capitulation. In 1997, Hawking raised the stakes beyond argument. At a conference at the California Institute of Technology, Hawking, alongside fellow physicist Kip Thorne, proposed a public bet with John Preskill, a quantum information theorist at Caltech. Preskill had spent years insisting the records survive. The terms were stark. If information escapes from a black hole, Hawking and Thorne lose. If information is permanently destroyed, Preskill loses. No hedge, zero ambiguity, and absolutely no path to graceful retreat for either side. One of the two most prominent physicists alive would be publicly, permanently wrong. Wrong about the most fundamental question in the field. Preskill accepted. The audience watched two careers placed on a single question, one that neither side possessed the tools to answer. Word of the bet spread through the community within weeks. The wager crystallized the abstract disagreement, turning decades of argument into something personal and permanent. two names on one question had a public record. Eventually, one of them would have to stand before the world and admit defeat. Susskind refused to concede, not from stubbornness but from the deepest kind of necessity. If a quantum state can evolve into two possible histories, then the probability rules holding quantum mechanics together stop functioning. Measurements lose meaning. Predictions become unreliable. Every chemical bond, every nuclear reaction, every piece of technology built on the assumption that quantum mechanics works, all of those results become suspect. Accepting information loss does not just break one equation. Accepting information loss breaks the foundation under all of physics. But Susskind faced a mirror problem. Curved space-time, the framework predicting the black hole boundary in the thermal radiation, had also never been wrong. Starlight bending near the sun, measured during eclipses since 1919. Slow orbital decay of binary pulsars, tracked for decades. Gravitational waves from merging black holes, captured by laser detectors in 2015. Every prediction confirmed to extraordinary precision. Every measurement consistent. Two pillars, both tested beyond any reasonable doubt, both successful everywhere else in the cosmos. And at the one location where both pillars apply, both deliver opposite verdicts about whether reality keeps a permanent record of what has happened. The fight was not about physics careers. The fight was about reality. If information can be permanently erased, then the universe does not maintain a continuous history. Every arrangement of every particle, from the first instant onward, becomes vulnerable to deletion, not just inside black holes. If the guarantee breaks at one boundary, the guarantee is broken at every boundary. Unitarity is either universal or unitarity is meaningless. And if unitarity is meaningless, then the continuous history connecting every moment to every other moment dissolves. Reality becomes something that can suffer permanent, irreversible amnesia. The war needed a judge, not another argument between geniuses who would never change each other's mind. A test, something so precise that neither side could argue with the outcome. In 1993, a physicist named Don Page proposed exactly that kind of test. Page was not at the center of the war. Working quietly at the University of Alberta, far from the conference halls where Susskind and Hawking collided, this physicist had taken a different approach entirely. No arguments about principles. No grand frameworks. Instead, 20 years spent on a single, narrow focus: the quantum connections between a black hole and the radiation escaping from that black hole. The approach was unfashionable. The field wanted grand resolutions, sweeping frameworks, elegant escapes from the paradox. Page wanted a number. Specifically, Page wanted to know the shape of a curve. If the quantum guarantee holds, if records truly survive, then a specific, measurable quantity, the entropy of the escaping radiation, must follow a specific path over time. Page asked that question and derived the answer. The answer was a curve, specific and exact. Early in the evaporation process, as the black hole radiates, the entropy of the radiation climbs. The radiation and the black hole become increasingly entangled. Disorder grows. But if records survive, then at a precise moment, the halfway point of evaporation, the entropy must peak. Then the entropy must begin to fall. The radiation starts carrying the record back out. Entanglement unwinds. By the time the black hole has vanished entirely, the entropy returns to zero, every record accounted for, every quantum state recovered. That shape became known as the Page curve. The Page curve was not a theory and not a prediction, a test. One single decisive test that could end the war permanently. Derive the curve from the mathematics of gravity and the records survive. The war ends. Fail to derive the curve and the war continues. Nobody has proven anything. For years, physicists attacked the problem from every direction. The Page curve became an obsession. Entire workshops were organized around the single goal of deriving that one shape from gravity. Blackboards at the Kavli Institute in Santa Barbara were covered in failed attempts. The equations stayed up for weeks, as though persistence alone might rearrange them into something that worked. Susskind tried and failed. Tooft tried and failed. Hawking, the architect of the original crisis, tried and also failed. String theorists built elaborate new frameworks. Researchers in quantum gravity invented new tools and aimed every tool at the problem. None of the attempts succeeded. The standard machinery of gravitational physics produced only a rising line, entropy climbing forever, with no peak and no decline. Gravity seemed to insist that records are destroyed. The page curve sat there year after year, the one shape the universe must trace if the universe truly remembers. Nobody could coax that shape out of the equations. The paradox devoured careers. Students entered graduate programs hoping to solve the puzzle. Those students became postdocs, then faculty. They watched their own students enter the same programs, chasing the same unanswered question. Some shifted to different problems entirely, exhausted by decades of failure. Some left the field. The physicist Joseph Polchinski, one of the sharpest minds in string theory, described the paradox as the problem he most wanted to solve before running out of time. Polchinski would eventually play a central role in shattering the comfortable answer. But that moment was still years away. Before the shattering came, the paradox outlasted an entire generation without yielding a single inch. Conferences ended with the same open questions they began with. Review articles catalogued the failed approaches and concluded year after year that no resolution was in sight. 20 years passed after Hawking's original calculation, then 30, then 40. Two pillars of physics delivering opposite verdicts. A single shape that would resolve the contradiction sitting unclaimed on the table, and nobody on Earth could produce the shape. Then, in 1997, a young physicist at Harvard named Juan Maldacena published a conjecture that shifted the ground. Maldacena proposed a bold equivalence. A theory of gravity operating inside a curved spacetime is identical to a quantum theory living on the boundary of that same spacetime. The boundary theory obeys unitarity without exception. No information loss, ever. If Maldacena's conjecture holds, then information must survive inside a black hole, because the boundary description keeps perfect records. The conjecture did not produce the page curve. Nobody could extract the decisive shape from Maldacena's equivalence, no matter how many different approaches they tried. But the conjecture tilted the confidence of the community sharply towards survival. By the early 2000s, most physicists believed the records survive. The belief was nearly unanimous. Belief is not proof, and the widespread belief created enormous pressure to explain the mechanism. The question was simple. What path does information take to escape from behind a boundary that nothing can cross? By what method does the thermal glow, the featureless hiss that Hawking proved carries no memory, somehow encode the complete history of every particle swallowed? The pressure produced an answer, an elegant framework that reconciled the contradiction by splitting the description into two perspectives, both valid. One observer watching from outside sees information escaping in the radiation, slowly over eons. Another observer falls through the boundary and notices nothing unusual. Both perspectives are correct. Both perspectives are real. A fundamental limit prevents any single observer from comparing both views at the same time. No contradiction, because no single vantage point can witness both truths simultaneously. That framework was called complementarity. An entire generation of physicists adopted complementarity as the resolution to the paradox. Research programs and graduate courses were built around the framework. The crisis appeared to be over. Except the crisis was never over. Physicists had chosen a side, overwhelmingly and with great confidence. The mathematics had not. The page curve, the one shape that would prove survival with the certainty of mathematics, remained underrun. Complementarity offered comfort. Complementarity offered coherence. Neither comfort nor coherence produced the curve. The records are either permanent or they are not. Nobody can show which. For 20 years, physicists thought they found a way out. They were wrong. The escape looked perfect. For a while, the escape looked absolutely perfect. In the early 90s, Leonard Susskind, along with Lars Thorlacius and John Uglum, proposed a framework so elegant, so satisfying, that physicists across the field adopted the framework as consensus within a decade. The idea was called black hole complementarity, and the core claim behind the framework was disarmingly, almost suspiciously, simple. Both sides of the information paradox are simultaneously correct. Quantum mechanics is right, and general relativity, the framework that governs gravity and curved space-time, is also right. The apparent contradiction between the two theories is not a real contradiction, because no single observer can ever catch the universe in the act of contradicting itself. Here is how complementarity works. Picture an astronaut falling toward a black hole, with a second observer watching from a safe distance far away from the horizon. According to general relativity, the astronaut crosses the event horizon and notices nothing at all. Space-time near the horizon is smooth and gentle, almost boring, calm and unremarkable to anything passing through. The astronaut sails inward, alive, unaware of crossing any boundary whatsoever. But the distant observer, watching from far away, sees a completely different and contradictory story unfolding at the same moment. From the outside, the astronaut never crosses the horizon. Instead, the astronaut slows down, redshifts toward invisibility, and smears across a thin membrane hovering just above the event horizon. Physicists call that membrane the stretched horizon. Every bit of information the astronaut carried gets absorbed into the membrane, scrambled beyond all recognition, and eventually leaked back out in the faint glow of Hawking radiation. From the distant observer's perspective, the information survives, and the quantum guarantee is preserved. The astronaut, measured from outside, is gone. Two stories. Two incompatible descriptions of the exact same event. One says the astronaut passes through unharmed. The other says the astronaut is absorbed, scrambled, and radiated back to the cosmos over billions of years, particle by particle. Both cannot be literally true at the same time. And here is the move that made complementarity so seductive. Both descriptions are valid because no single observer can ever verify both descriptions simultaneously. Think about why the verification is impossible. The astronaut who crosses the horizon cannot turn around and send a report back. Communication outward across the event horizon is forbidden by the geometry of space-time. Meanwhile, the distant observer cannot dive in to check, because diving in means becoming an infalling observer and losing the outside perspective permanently. And quantum mechanics already contains a strict rule, called the no-cloning theorem, that forbids duplicating quantum information. A quantum state cannot exist in two copies at once, so the universe never actually contains two versions of the astronaut. One observer sees one version, a different observer sees a different version, and no experiment, no clever trick, no measurement can ever place both versions in front of the same pair of eyes. The proposal was not a compromise. The proposal was an assertion that the contradiction does not exist because the structure of space-time forbids any single witness from ever observing both outcomes. No contradiction, no paradox, not a single broken law of physics. The escape preserved quantum rules for the quantum physicists and smooth horizons for the relativists. And the framework asked nobody to give up a foundational principle. But remember the stakes. Every atom in the universe carries a record. Every collision, every exchange of energy, every quantum interaction that has ever occurred. If complementarity fails, those records face permanent destruction, and the laws governing every molecule in the cosmos crack at the foundation. The resolution was clean, logically airtight, and profoundly reassuring. A wound in the foundations of physics that had been bleeding for 20 years appeared, finally, to be healed. Susskind would later describe the collective feeling as relief. Relief so deep that physicists stopped asking questions, stopped probing for weaknesses, and simply assumed the crisis was over. And the healing did not rest on complementarity alone. 4 years after Susskind's proposal, a young physicist named Juan Maldacena published a result, and the result sent shockwaves through every corner of the field. Maldacena discovered an equivalence so unexpected, so clean, that many physicists initially refused to believe the equivalence could be exact. A theory of gravity operating inside a particular type of curved space, called anti-de Sitter space, is mathematically identical to a quantum theory on the boundary of that space, not roughly identical, not similar under specific conditions. Identical in every detail, down to the last decimal place. And the reason the correspondence shook the field comes down to a single property. The boundary theory is a standard quantum theory, and standard quantum theories preserve information by construction. The quantum guarantee is woven into the boundary theory at the deepest level, not bolted on as an assumption, but derived from the mathematical structure. Because the boundary theory is exactly equivalent to the gravitational theory, the gravitational theory inherits the guarantee automatically. Information cannot be destroyed in the gravitational description, because destroying information would mean destroying information in the boundary description, and the boundary description forbids destruction as a mathematical law. Maldaceno's correspondence did not merely support complementarity. The correspondence seemed to bury the entire debate. And in 2004, Hawking himself publicly conceded the bet with John Preskill. Standing before a packed audience at a conference in Dublin, Hawking acknowledged that information likely survives black hole evaporation. The concession was public, deliberate, and final. Hawking handed Preskill an encyclopedia of baseball, a symbol that all the information inside could, in principle, be recovered from the radiation of a black hole. Headlines ran worldwide. Physicists who had spent decades arguing about whether information survives allowed themselves, for the first time, to exhale. So the field moved forward with a speed and confidence that would prove deeply premature. Graduate students entered programs studying the boundary correspondence. Entire research institutions assumed information survival as established fact. Conferences shifted focus from debating whether information survives to mapping the mechanism of survival. A generation of physicists built careers on the confidence that the crisis had ended. Complementarity handled the observer paradox. Maldaceno's correspondence supplied the mathematical backbone. Together, the two frameworks formed a fortress that seemed permanent and invulnerable. For nearly 20 years, no attack breached the walls. But here is the vulnerability of fortresses. A fortress is only as strong as the assumptions holding the walls together, and assumptions, unlike theorems, have a dangerous property. Assumptions can harbor contradictions that go unnoticed for decades, precisely because nobody thinks to test the assumptions. The longer an assumption goes untested, the harder the fall. In 2012, 4 physicists walked through the front door of that fortress, and using nothing but the logic the fortress was built from, burned every wall to the ground. Ahmed Al-Meri, Donald Maroff, Joseph Polchinski, and James Sully were not outsiders launching an attack from beyond the walls. All 4 worked within the framework the community had accepted for 2 decades. All 4 used the same tools, the same mathematics, the same assumptions that everybody else used. And the approach the 4 researchers took was not exotic or revolutionary. The approach, in fact, was almost embarrassingly direct. Al-Meri, Maroff, Polchinski, and Sully examined the 3 core assumptions of complementarity and asked a question that, in hindsight, somebody should have asked 20 years earlier. Can all 3 assumptions hold simultaneously for an old black hole, one that has already radiated away more than half of the original mass? The 3 assumptions are straightforward. First, the quantum guarantee. Information is preserved, and the rules hold without exception in the full theory. Second, effective field theory. The known laws of physics work normally outside the horizon, in regions where gravity is weak and space-time curvature is mild. Third, the equivalence principle. An observer falling through the horizon notices nothing unusual, experiences smooth passage, encounters no wall and no disruption. For a young black hole, one early in the evaporation process, all 3 coexist without conflict. The young black hole has not radiated enough energy at that stage to create any tension between the 3 assumptions. But for an old black hole, one past the halfway point of the page curve, the 3 assumptions collide head-on. And the collision is not a subtle tension or a philosophical discomfort. The collision is a proven logical impossibility, derived with the same rigor as any theorem in quantum mechanics. Here is the argument, stripped to the bone. After the halfway point of evaporation, the Hawking radiation that has already escaped must be entangled with the radiation still emerging. The quantum guarantee demands that entanglement. The early-late correlation is what allows the page curve to turn, to fall back towards 0. Without the correlation between early and late radiation, information is permanently lost. The curve rises forever, exactly as Hawking predicted. So the quantum guarantee requires the escaping particle at every stage to be entangled with particles that escaped earlier. But effective field theory demands a competing entanglement. Each new particle escaping the horizon is born as half of the pair. One particle flies outward, carrying positive energy. One falls inward, carrying negative energy. The pair is entangled by the same mechanism that created the pair, and that pair-level entanglement is what keeps the horizon smooth. Remove the bond between the outgoing particle and the infalling partner, and the quantum vacuum at the horizon falls apart. The smooth fabric of space-time at the boundary unravels. The disruption produces a wall of fierce radiation at the horizon, a firewall violent enough to incinerate anything that approaches. And now the trap closes. A single quantum of escaping radiation cannot, under any conditions, be maximally entangled with two different systems at once. Quantum mechanics forbids the arrangement completely. Physicists call the property monogamy of entanglement. The property admits zero exceptions under any conditions in any theory that respects quantum mechanics. So the escaping particle faces a forced choice: stay entangled with the early radiation, preserving the quantum guarantee, allowing the page curve to fall, or stay entangled with the infalling partner, keeping the horizon smooth, preserving the equivalence principle. Choose one, lose the other, and no clever workaround can avoid the choice. The forced decision is a consequence of mathematical law, not physical circumstance. Three foundational principles stand in conflict: the quantum guarantee, effective field theory, and the equivalence principle. Every physicist in the field believed all three. Harry, Marov, Polchinski, and Sully proved that at most two can hold at the same time. Pick any pair, and the remaining principle must break. And breaking any one of the three is catastrophic, with consequences that cascade through all of physics. Drop the quantum guarantee, and quantum mechanics cracks at the base. The framework governing every atom, every molecule, every chemical bond in the known universe would suddenly fail the moment gravity grows strong enough. Drop effective field theory, and the familiar laws of physics break in a place where gravity is gentle, which means those laws could break anywhere. Drop the equivalence principle, and general relativity is wrong at the event horizon. But here is what makes that option so painful. The horizon of a large black hole is among the calmest regions in the cosmos. Tidal forces at the horizon of a supermassive black hole, measured carefully, are gentler than the forces you feel standing on Earth. If physics breaks in a region that calm, physics breaks for reasons that nobody can identify or explain. For 2 decades, the field had been sleeping under a blanket that turned out to be tissue paper. The escape was not a solution. The framework was a postponement. A contradiction had been hiding inside the logic all along, concealed behind an assumption nobody checked, the assumption that the logic holds for old black holes past the halfway mark. The comfortable escape, the framework that an entire generation had trusted as settled physics, had been logically impossible from the very beginning. And here is the dark comedy buried in the wreckage. Thousands of physicists across 2 decades had built entire research programs on the framework. Thousands of papers extending the framework, prizes awarded for discoveries within the framework. And a fatal contradiction had been present the entire time, waiting for someone to ask one obvious question: does the argument survive past the halfway point? The universe, as a rule, does not award points for elegance. Accuracy is all that survives, and the framework was elegant, widely accepted across the field, and profoundly wrong. The firewall paper landed like a detonation. The physics community, which had assumed the crisis was closed, discovered overnight that the crisis had never been closed at all. Conferences erupted. Physicists who had built reputations on complementarity found themselves, overnight, defending a position that 4 colleagues had just proven untenable. Some researchers proposed accepting the firewall as physical reality. Under that proposal, black holes do not have smooth horizons at all. Black holes have walls of fire at the boundary, burning through every particle that falls in. The proposal saves the quantum guarantee and effective field theory. but murders the equivalence principle, one of the bedrock commitments of general relativity. Others proposed modifying effective field theory. Under that view, quantum gravity effects extend much farther from the center than previous calculations assumed. In that scenario, the known laws of physics break down in a region where gravity is weak, a region where every particle physics experiment ever conducted says the laws should hold perfectly. Still, others return to the original position Hawking had defended for decades. Perhaps the quantum guarantee is the casualty, and quantum mechanics needs modification when gravity enters the picture. Every option was a disaster. Every option required surrendering a principle that the rest of physics cannot function without. And for 7 years, the field froze. Papers continued to appear, but none of those papers moved the needle even slightly. Ideas were proposed and abandoned within months. Workshops convened across 4 continents, and none produced a resolution. Senior physicists who had spent careers building the consensus framework found themselves starting over with no clear direction and no obvious path forward. The firewall trilemma sat at the center of theoretical physics like a locked door, and nobody possessed the key. Polchinski, one of the 4 authors of the firewall paper, described the situation as the sharpest paradox in the history of the field. The field was paralyzed. And the paralysis was not the quiet kind. The paralysis was the kind that comes from knowing with certainty that every available option is worse than the problem. But during the paralysis, one idea arrived that felt different from every other attempt. Not because the idea solved the firewall problem, the idea left the firewall problem untouched. What made the idea feel different was the direction the idea pointed toward a place nobody had looked before. In 2013, Maldacena and Susskind proposed a conjecture so sweeping, so audacious, that even the 2 authors marked the conjecture as speculation. The proposal was simple to state and enormous in scope. Einstein-Rosen bridges, the geometric passages through curved spacetime that physicists call wormholes, might be the same phenomenon as quantum entanglement. Geometry and connection, the curvature of spacetime, and the invisible bond between distant particles. 2 seemingly unrelated pillars of physics. 2 concepts that appear to describe completely different features of reality might, at the deepest level, be one and the same. The conjecture carries a name built from 2 landmarks in physics, the Einstein-Rosen bridge on one side, the Einstein-Podolsky-Rosen paradox on the other. Einstein's name appears on both sides because the same physicist who first described the geometry of curved space-time back in 1915 also first described quantum entanglement. And a century later, 2 researchers proposed that those 2 discoveries were always the same discovery, viewed from opposite directions. Here is what the conjecture proposes in concrete terms. Take 2 particles that are quantum entangled, measure one, and the measurement instantly determines the state of the partner, regardless of the distance separating the 2 particles. The link does not carry signals. The link does not violate the speed of light. But the link is experimentally real, confirmed beyond doubt in laboratories around the world. The conjecture says the link is a wormhole, not a tunnel large enough for a spacecraft to pass through. A microscopic geometric structure woven into the fabric of space-time, connecting 2 locations through a passage that does not cross the space between those locations. Entanglement creates geometry. Geometry encodes entanglement. Destroy the entanglement and the geometric link ceases to exist. Strengthen the entanglement and the geometric link grows stronger. And the consequences cascade outward. If every entangled pair is connected by a geometric thread, and if particles escaping a black hole are entangled with particles trapped inside, then the interior of every evaporating black hole is connected, through geometry alone, to the exterior by a vast web of wormhole threads. The barrier between inside and outside is not a wall. The barrier is a mesh, each thread linking a piece of the interior to a piece of the escaped radiation. Information does not need to punch through the horizon because the information never truly passed behind a barrier. Every quantum record is already connected to the exterior through the geometric fabric of space-time. What looks like a wall from the outside is actually a web of connections reaching outward into the cosmos. The vision was extraordinary. consistent with the boundary correspondence that Maldacena had discovered years earlier, aligned with known results about the deep relationship between entanglement and geometry, and not obviously contradicted by the firewall argument, which was a rare achievement given how effectively the firewall destroyed every other proposal. The conjecture offered a picture of reality where space, distance, and separation are not fundamental features of the universe. Instead, space emerges from connections between quantum systems. Sever those connections, and the fabric of space rips apart entirely. Strengthen those connections, and space becomes smooth. The geometry of the cosmos arises from quantum links between particles, the way the surface of a lake arises from the collected motion of molecules beneath. For 6 years, the conjecture fueled an ambitious and wide-ranging research program. Physicists mapped new and surprising relationships between geometry and quantum information. Fresh mathematical tools were developed, built specifically to probe the boundary between entanglement and space-time. Insights about the deep structure of space-time accumulated steadily, one careful calculation at a time. And through all of the progress, through every breakthrough and every conference talk and every journal publication, one stubborn and deeply uncomfortable fact refused to yield. The conjecture could not produce the page curve, that specific shape, the one curve that everybody agreed was the only decisive test of information survival, the one shape that any valid resolution must reproduce, derived from a gravitational calculation. The conjecture was beautiful, profound, and powerfully suggestive, but the conjecture could not generate the one number, the one shape that the crisis had demanded for over 2 decades. The shape is still the test. Nobody has produced the shape from a gravitational calculation. The crisis is still open. And the longer the shape remained beyond reach, the more painful the gap between beauty and proof became. The conjecture told the field what the answer should look like, but telling is not the same as proving. And in physics, a vision without a derivation is a conjecture, no matter how beautiful the vision may be. And so the field stood at the close of 2018, paralyzed between dead ends. Complementarity shattered. The firewall trilemma, admitting no resolution that does not destroy a foundational principle. The wormhole entanglement conjecture, a vision of breathtaking beauty that cannot produce a single number on a graph. Every escape from the paradox had failed. Every proposed resolution, without exception, had opened a worse problem than the one the resolution was meant to fix. And the tools needed to break the deadlock, the tools that could actually derive the page curve from gravity, was sitting quietly in the existing mathematical literature, available to anyone who looked, untouched, waiting. The most beautiful idea in physics cannot produce the one number the crisis demands. The tools to produce that number already exist. Nobody has picked them up. Those tools have been waiting since 2006, sitting in the published literature available to every researcher in the field, untouched for over a decade. And while an entire generation of physicists exhausted themselves against a wall, the instruments capable of dissolving that wall collected dust on a shelf. That is the part of this story that lands hardest, not the crisis itself. The dead ends are not the tragedy either. What hits hardest is the realization that the answer was already there, sitting in plain view, and nobody reached for the answer. Consider the state of the field at the close of 2018. Every exit was sealed. Complementarity, the comfortable framework that an entire generation trusted as settled physics, had been destroyed from within by 4 researchers wielding the framework's own logic. The firewall trilemma sat at the center of the discipline like a locked vault, demanding that at least one foundational principle must break, while offering no guidance about which sacrifice would cause the least damage. The conjecture, linking wormhole geometry to quantum entanglement, had pointed toward a profound structural connection, but could not produce the single number that the crisis demanded. Beautiful as a vision, powerless as a proof. At the page curve, the one shape that the entire community agreed was the decisive test, the proof of whether information survives, remained beyond reach. By 2018, 25 years had passed since Don Page proposed the curve. Not a single gravitational calculation had reproduced the shape. An entire generation of graduate students who entered programs as 22-year-olds had built full careers around the paradox. Some of those researchers were approaching retirement, and the question Hawking raised in 1974 remained wide open. 44 years, no resolution. The wound in the foundations of physics would not heal. Except somebody did possess the instrument. Multiple people possessed the instrument. The instrument had been published, peer-reviewed, celebrated, and taught in graduate courses for 13 years. But nobody had picked the instrument up and aimed at the right problem. So here is the question that demands an answer. How does a field of thousands of brilliant researchers miss a tool sitting in the open, not through stupidity, not through carelessness, through a deep and human pattern in how scientific communities organize knowledge? When a tool is developed in one context, researchers file the tool mentally under that context. The filing is unconscious. Once a tool has a label, the label sticks and the tool becomes invisible to anyone working under a different label. That is exactly what happened here. One label belonged to the formula and the applications built on that formula. A completely different label belonged to the crisis, and for 13 years, nobody thought to peel the labels off. Rewind now to 2006. In Santa Barbara, California, two physicists named Shinsei Ryu and Tadashi Takayanagi publish a formula connecting two seemingly unrelated quantities. On one side of the equation sits entanglement entropy, measuring how much quantum information a region shares with the rest of the system. A pure quantum quantity expressed in bits. On the other side of the equation sits the area of a specific surface anchored in the deeper geometry of the bulk spacetime. Entanglement, a quantum property measured in bits linked to area, a gravitational property measured in square meters. One formula bridging two frameworks, quantum mechanics and gravity, that the information paradox had placed in direct opposition. The result is recognized as significant almost at once, and the formula is clean, exact, verified by multiple independent groups within months of publication. Physicists across 4 continents adopt the Ryu-Takayanagi formula rapidly. Within a few years, the formula becomes a standard instrument in the quantum gravity toolkit. Research groups apply the formula to calculate entanglement in boundary theories, to probe the interior geometry of curved spacetimes, and to map the deep relationship between quantum information and the shape of space. Hundreds of papers build on the result. Entire conference sessions are devoted to the formula, exploring what the formula reveals about the bond between information and geometry. Prizes follow. Careers are shaped by insights drawn from the formula. Nobody aims the formula at the problem of black hole radiation, not once in 13 years. The information paradox, at the deepest level, is a question about entanglement entropy. Does the entanglement entropy of Hawking radiation follow the Page curve, rising then falling, or does the entropy rise forever? That is the entire 50-year crisis, compressed to a single measurement. And the Ryu-Takayanagi formula is, at the deepest level, an instrument for calculating entanglement entropy using geometry. A formula designed to measure exactly the quantity that the crisis hinges on, and a crisis defined entirely by that same quantity. Both existed in the same community, cited in the same journals, discussed at the same conferences, and for 13 years, nobody connected the two. Part of the reason for the disconnect is structural. The original Ryu-Takayanagi formula applies in static settings, timeless snapshots of systems sitting in equilibrium. Black hole radiation is the opposite of static. With every single escaped particle, the black hole shrinks by a tiny fraction of mass. Radiation builds outside the horizon. The entanglement pattern shifts with every quantum of energy that escapes the boundary. To apply a formula built for frozen snapshots to a dynamic process, one that unfolds over billions of years, physicists need a more general version, one that folds in quantum corrections and accounts for geometry that evolves over time. That more general version also existed. In 2014, Netta Engelhardt and Aaron Wall published an extension of the Ryu-Takayanagi formula that includes quantum corrections. The extension handles situations that change over time, and the extension folds in quantum effects occurring in the bulk of space-time. Physicists named the upgraded version the quantum extremal surface prescription. The name comes from what the formula does. The formula identifies a special surface in space-time, a quantum extremal surface, where the combined contribution of geometric area and bulk entropy reaches a critical point. A surface that balances geometry and quantum effects at once in a setting that evolves. And even after the extension arrived, nobody aimed the refined tool at the paradox. Not for 5 more years. 5 years of the field laboring under the firewall crisis, with the instrument to resolve the crisis sitting in the same literature. During those 5 years, the community was anything but idle. Research programs ran at full speed across dozens of institutions. Some groups chased ER equals EPR, trying to extract the page curve from the connection between wormholes and entanglement, searching for a derivation that would turn the beautiful conjecture into a rigorous proof. Others constructed models of information recovery using simplified toy systems, hoping to capture the essential physics without the full complexity of realistic black holes. Still others probed the firewall argument from every angle, turning the paradox over and over, hunting for loopholes that turned out not to exist. Each approach was ambitious and creative, yet each approach was aimed at the wrong target. Because the right target required picking up a tool that the community had already catalogued, cited, and mentally filed in a separate category. One category held applications of holography. A completely separate category, with no overlap, held the black hole information crisis. Researchers in the first category did not think to apply the tools to the second, and the conceptual door between those two bodies of research, a door that required only a single insight to open, stayed closed for over a decade. Until May of 2019, and what opens next is the kind of moment, rare and irreversible, that physics produces once or twice per century. A moment where the decades of preparation, the slow accumulation of tools and insights and failed approaches suddenly crystallize into a single breakthrough that changes the shape of the entire field. What happened is, by any fair accounting, one of the most remarkable convergences in the history of modern physics. Jeffrey Pennington, a graduate student at Stanford University, submits a paper to the physics preprint server. Pennington had been studying the quantum extremal surface prescription for months, probing the formula's behavior in different settings, testing whether the mathematics could handle the complexity of a shrinking black hole. The question driving the work was precise. Could the existing geometric tools, applied carefully to Hawking radiation, reproduce the one shape that the field demanded? The paper lays out a new approach to calculating the fine-grained entropy of Hawking radiation, built on the quantum extremal surface prescription. Pennington does not invoke exotic new physics. Pennington does not appeal to speculative conjectures. Instead, Pennington takes two existing tools, the Ryu-Takayanagi formula and the quantum extremal surface extension, and applies those tools with care and precision to a model of a black hole losing mass through Hawking radiation. On the same day, a separate group of 4 physicists submits a paper reaching the identical conclusion through the identical tools. Ahmed Al-Naheri, based at the Institute for Advanced Study, had been circling the same question from a different angle. The conviction driving Al-Naheri was specific. The firewall crisis contained a gap in calculation, not in concept. Netta Engelhardt at Princeton recognized something that, in hindsight, should have been obvious years earlier. Engelhardt was one of the original architects of the quantum extremal surface extension, and the tools she had co-created in 2014 might reach further than anyone had tested. Donald Marolf and Henry Maxfield, working from Santa Barbara, brought deep expertise in the gravitational path integral, the very framework that would anchor the Fuller derivation months later. 4 researchers, each carrying a different piece of the puzzle, converged on the same calculation independently. Neither Pennington nor the 4-person group knows the other exists. Neither group has seen the other's work. Both papers appear on the preprint server within hours of each other, submitted from opposite coasts of the United States on the same day. 2 independent groups working on opposite coasts of the United States. Identical tools, identical answer, submitting on the very same day, within hours of each other. That kind of convergence does not happen by accident. When 2 separate teams, with no communication between them, arrive at the same destination through the same instruments on the same morning, The convergence signals a deep truth about the problem. The answer was ripe. The groundwork laid across 13 years of tool building had brought the solution to the surface, and both groups simply reached down at the same moment. Here is what both groups found. And the result, once you understand the result, is the kind of breakthrough that makes the decades of failure feel almost necessary. Because without the despair, without the dead ends, without the slow accumulation of tools and techniques across 13 years, the result would not exist. The answer required the preparation. And the preparation was, in hindsight, every tool and technique the field had been building toward without knowing the destination. When the quantum extremal surface prescription is applied to a shrinking black hole, the formula does not identify one candidate surface for the entropy calculation. The formula identifies two. Early in the process, when the black hole is young, having shed only a small fraction of the original mass, the first surface sits near the boundary of the black hole. Entropy calculated from that surface rises with each escaped particle climbing steadily higher. The curve matches Hawking's original prediction precisely. Nothing new, nothing surprising. Entropy goes up, and entropy keeps going up, exactly as the thermal calculation demands. But after a critical moment arrives, roughly when half of the original mass has radiated away, a second surface appears in the formula. And that second surface sits in a place nobody expected. Inside the black hole. A surface located inside the event horizon, in a region from which no signal can escape, becomes the dominant contributor to the entropy calculation for the radiation outside. According to the formula, the interior region bounded by that surface belongs to the radiation's entanglement wedge. What does that mean in plain terms? Information encoded within that interior region is not trapped behind the horizon. The quantum extremal surface prescription declares, through the geometry of the surface, that the interior information is already part of the external radiation, not will eventually become part of the radiation. Already is. Physicists named that interior region the island, an island of space-time, physically located inside the black hole, separated from the exterior by the event horizon, yet connected to the radiation outside through the entanglement structure captured by the geometric formula. No particle crosses the barrier to deliver the information, and no signal escapes the horizon. Light cannot punch through. The connection does not operate through any classical channel or any physical tunnel. Instead, the connection exists in the quantum state, encoded in the geometry that Ryu and Takayanagi first described 13 years before. Every generation of physicists since Hawking had accepted one assumption without question: the event horizon draws an absolute line, and nothing encoded behind that line can ever reach the exterior. The island dissolves that assumption completely. A region physically located inside the black hole belongs, in terms of quantum information, to the outside. The boundary between trapped and free is not where anyone assumed. Consider an analogy. Imagine a locked vault with no doors and no windows. For decades, everyone assumes the contents of the vault are inaccessible. Permanently sealed, engineers inspect every surface. No crack, no seam, no channel of any kind penetrates the barrier. The contents are gone, the experts say. Whatever is inside will never be known. Then someone discovers that the walls of the vault, despite appearing solid, have been broadcasting the contents to the outside world the entire time. Not through a hole or a crack in the surface, through the structure of the walls. The atoms composing the barrier vibrate in patterns shaped by the objects within, and those vibrations radiate outward continuously, carrying a complete record encoded in the pattern of the trembling. Every detail is present in the signal. The broadcast was always happening, from the very first moment the vault was sealed. Nobody knew to look for the signal because nobody suspected a signal existed. That broadcast is the island, and the event horizon is not a wall. Instead, the horizon is a membrane that has been transferring information outward through the entanglement structure of the quantum state since the first particle escaped. And the island changes the entire calculation. Before the page time, only one surface contributes. Entropy climbs. Hawking's prediction holds perfectly. After the page time, the island surface takes over because the island surface yields a lower entropy value. And the quantum extremal surface prescription contains a built-in rule when two candidate surfaces compete. The surface with the lower entropy wins. Always. That rule is not a judgment call. The rule is a built-in instruction encoded in the mathematics. So after the page time, the entropy of the radiation stops climbing. Each new particle escaping the black hole no longer adds confusion to the external state. Instead, each new particle is already accounted for by the island, which captures the entanglement structure of the interior. Correlations begin appearing in the radiation. Patterns emerge between particles that escaped decades ago and particles escaping now. Pieces of the puzzle click together. Confusion decreases. Order builds. The entropy curves downward steadily as the black hole continues to shrink. When the black hole finishes radiating away every last fraction of mass, entropy returns to zero. Every quantum record that ever crossed the horizon is now encoded in the radiation outside. Each bit of information is accounted for. Each trace of each object that ever fell in has been transferred, woven into correlations between billions of radiation particles scattered across space. Every piece is in place. The picture is whole. And there, emerging from the calculation, sits the page curve, derived from gravity for the first time. 26 years after Don Page proposed the shape, 45 years after Stephen Hawking's calculations split physics in two, the specific curve that the entire field accepted as the decisive test, the shape that no gravitational approach had been able to generate, emerged cleanly from a calculation using tools available for over a decade. And here is the moment that carries the weight of the entire story. The shape that nobody could produce for 26 years. Two people produced the shape on the same day. Records survive. The universe does not forget. And every physicist who had spent a career under the shadow of that question at last had proof. For 45 years, the possibility of permanent erasure hung over physics like a sentence with no appeal. Entire careers began and ended inside the shadow of that open question. Graduate students who entered the field as 22-year-olds retired without seeing resolution, without ever knowing whether the universe keeps permanent records. Researchers built entire frameworks to survive the crisis and watched those frameworks shatter. The firewall argument 7 years earlier had sealed every comfortable exit. A field of thousands was left with no path forward, no reason to believe a path existed. And then, on a single day in May of 2019, the shadow lifted, not gradually, not through a slow build-up of partial results. In one stroke, two papers, same tools, same curve, same day. The wound that had bled for nearly half a century finally closed in the span of a single afternoon. The reaction in the physics community was immediate and volcanic. Papers poured in within weeks. Groups at universities across 4 continents rushed to verify the calculation, to extend the result, to test whether the island formula held up under every variation, every edge case that decades of paradox work had generated. Conference talks pivoted overnight toward mapping how information escapes, rather than debating whether information escapes at all. Researchers who had spent careers in the shadow of the paradox experienced for the first time the sensation of standing on solid ground. And the closing carried a particular sting for anyone who had been in the field long enough to feel the irony. The crisis persisted not because the physics was missing, but because the connection between existing physics was missing. But the derivation demanded deeper grounding. The island formula works and the page curve emerges cleanly from the calculation. And yet, a formula that works is not the same as a formula that is understood. Why does the island appear? What mechanism in the underlying physics produces a surface inside the black hole that contributes to the entropy of radiation outside? Is the formula a lucky shortcut that happens to generate the correct shape? Or can the formula be traced back to first principles, to a deeper layer of the gravitational theory that explains why the island must exist? Late in 2019, 2 groups answered those questions. And once again, both groups worked in parallel without knowing about each other. Aumheri, Hartman, Maudhasina, Shaghulian, and Tajdini published one derivation. Pennington, Schenker, Stanford and Yang published another. Both groups used a technique from statistical physics called the replica trick, adapted to the gravitational path integral. Here is the core idea in plain language. The gravitational path integral is a procedure for calculating physical quantities in quantum gravity. That procedure works by summing over every possible geometric shape that space-time could take, with each shape receiving a weight that depends on the geometry. Think of the procedure as posing a single question. What are all the ways that space could curve? And how much does each curved shape contribute to the final answer? Add up every contribution, and the sum produces the result. When both groups applied the replica trick to that sum, a new class of geometric shapes appeared. Shapes that had never been included in previous calculations because nobody had searched for those shapes. Physicists named the new contributions replica wormholes. A replica wormhole is a geometric passage connecting different copies of the black hole used in the calculation. And here is the crucial distinction. Those copies are not real black holes sitting side by side in space. The copies are abstract tools used in the replica trick to compute entropy, a standard technique borrowed from statistical physics. But the geometric passages connecting the copies, the wormholes threading through the calculation, are genuine contributions to the gravitational sum. After the page time, those contributions become dominant. What rides on whether those contributions produce the right shape is the entire 50-year crisis. If the curve rises forever, Hawking wins. Every record that crosses a horizon is destroyed permanently. The laws governing every atom in the cosmos contain a fatal exception. 50 years of crisis end in defeat. Here is the timeline. Before the page time, standard geometric shapes dominate the sum. Contributions from replica wormholes are negligible, too small to change the answer. Entropy rises steadily, matching Hawking's prediction. After the page time, replica wormhole contributions overtake the standard shapes. The sum shifts dramatically, entropy stops rising, and the curve begins to fall back towards zero. So, replica wormholes provide the mechanism that justifies the island. The island is not a lucky accident or a convenient shortcut that happens to give the right answer. Instead, the island emerges from the gravitational sum when all relevant geometric contributions are properly included. Previous calculations missed the page curve. Why? Because those earlier calculations excluded the specific shapes that dominate at late times. Nobody excluded the shapes deliberately. Nobody knew the shapes existed. Hawking's original result was never wrong in any technical sense. Hawking's result was incomplete, capturing the early phase with perfect accuracy, but missing the contributions that take over after the midpoint, the contributions that bend the curve back towards zero. Entropy rises, peaks at the page time, and falls back to zero, exactly as Don Page predicted. What 2019 added was not a new ingredient. What 2019 added was the act of combining existing ingredients and pointing the combination at the right target. The derivation uses no exotic physics, invokes no speculative conjectures, and rests entirely on the gravitational path integral. Applied completely for the first time. The reaction from the broader physics community confirmed the weight of the result. Within weeks of the two papers appearing, research groups across a dozen countries began testing the island formula. Every edge case the paradox had generated over 5 decades became a target. Could the formula handle charged black holes, where the electromagnetic field adds a layer of complexity to the radiation spectrum? Yes. Could the formula handle rotating black holes, where the dragging of space-time near the horizon complicates the geometry? Again, yes. Physicists at the Kavli Institute for Theoretical Physics in Santa Barbara organized an emergency workshop, pulling researchers from 3 continents into a single room to map the implications. At that workshop, Raphael Busso, a former student of Hawking, presented a broader version of the island formula that extended the result to cosmological settings. Space-times that look nothing like the interior of a black hole. The formula held there too. Every test confirmed what the original derivation suggested. The island was not a trick specific to one model. The island was a structural feature of quantum gravity. and the robustness of that feature reshaped the direction of the field overnight. Research programs that had spent years circling the firewall problem pivoted within months. Graduate students who had entered programs expecting to spend careers on the paradox found themselves suddenly working on a problem that had an answer. Senior physicists, veterans who had watched the crisis outlast entire careers, described the shift in language reserved for rare moments in the history of the discipline. The ground had moved permanently, and every researcher in the field could feel the shift. Entire research agendas built around debating whether information survives were suddenly obsolete. Nobody could dispute the derivation. Proof was sitting on the preprint server, verified by independent groups within weeks, and no physicist anywhere on Earth could find a flaw in the mathematics. Conferences that had spent decades debating the survival question, year after year, now redirected toward a different problem entirely, not whether records survived. That question was answered. A harder question had taken the place of the old one, forced open by the very machinery that produced the answer, and the weight of that harder question would soon prove heavier than the original crisis. Because the gravitational path integral, the procedure generating the correct curve, carries a feature that nobody expected and nobody can yet explain. The procedure does not describe one universe. Instead, the procedure describes a sum over many possible configurations of space-time, each weighted by the geometry. And the meaning of that sum, whether the sum represents a single reality or an average over many, remains wide open. Pennington made the connection. Aumheri, Engelhardt, Maroff, and Maxfield made the same connection, working independently on the same day. And the months that followed proved the connection was not fragile. The connection was load-bearing. But the machinery producing the correct answer carries a cost, and the cost is not small. The gravitational path integral, by construction, does not select a single geometry as the real one. The procedure averages over geometries, and a procedure that averages over geometries may not be describing one specific universe. The machinery producing the answer may not describe a single reality. So the answer works. Records survive. The page curve confirms the survival. But the machinery that produced the answer has cracked open a question that nobody anticipated. Not a minor footnote. A question about the meaning of distance, of separation, of the very fabric that holds the cosmos together. The gravitational path integral averages over geometries. The procedure, by design, does not select one shape as the real one. Every possible curvature receives a weight, and the final answer sums across all of those weighted shapes. Does that sum describe one universe, the actual cosmos, where specific events happen in a definite order? Or does the sum describe a statistical blend of many possible universes, each with a slightly different shape, whose collective behavior produces the curve? Researchers debate the answer fiercely, and the debate touches the most foundational question in all of physics. Does reality have one definite shape, or does observation sample from a blend of many? Nobody has settled that question. The tools are too new, too recently forged in the heat of the paradox. The implications reach too deep, and the 50-year contradiction, having been resolved on one level, has opened an entirely new level of uncertainty. But the strangeness does not stop at whether one reality exists or many. The strangeness reaches deeper, much deeper. Consider what the replica wormholes actually require. The full resolution of a 50-year paradox depends on connections between copies of a system, copies that exist nowhere in the physical universe, linked by passages that no particle could traverse. Nobody chose to include those wormhole terms. Nobody inserted the terms by hand. The gravitational path integral, computed honestly and without prejudice, generates those terms on the procedure's own. Previous calculations missed the contributions entirely. The terms were always present in the mathematics. For decades, nobody thought to look for the terms, because nobody realized those particular shapes contributed to the answer. And the contributions are not a minor correction. After the page time, replica wormholes dominate the entire calculation, overwhelming every other term in the sum. Remove those connections, and the entropy climbs forever. Hawking's original prediction returns in full force. Information is lost. The entire 50-year paradox reopens, and every fraction of progress vanishes. So, the single most important number in the entire contradiction, the number the field demanded for half a century, depends on abstract connections that no particle could traverse. What do those connections mean? What do the wormhole terms, taken seriously as features of the underlying physics, imply about how reality is organized? That question, as the physics community would discover over the following years, reaches further than anyone anticipated. Go back 6 years before the page curve derivation. In 2013, Juan Maldacena and Leonard Susskind proposed a conjecture that seemed, at the time, almost too elegant to trust. The conjecture refers to two famous papers from 1935, both bearing the name Albert Einstein. One paper, by Einstein and Rosen, describes bridges through curved space-time, passages connecting two distant points through a shortcut in the curvature. The other paper, by Einstein, Podolsky, and Rosen, describes a persistent correlation between particles, a bond that holds regardless of how much distance separates the pair. Two papers from the same author, published the same year, two phenomena that physics had treated as entirely unrelated for nearly 80 years. Maldacena and Susskind proposed a radical identification, not that the two phenomena are merely analogous, or that the two phenomena share some limited formal similarity. The proposal was far stronger. Wormholes and quantum correlation are the same physical phenomenon described in two different languages. A bridge connecting two regions of the cosmos, according to the conjecture, is equivalent to the invisible bond connecting two systems. Every correlated pair of particles, in principle, shares a microscopic wormhole, and every wormhole represents a bond between the regions the passage connects, a thread in the larger web. The shape of the cosmos equals a pattern of correlations between distant particles. If the conjecture holds, then the two pillars of physics are not separate descriptions of separate domains. The two pillars are two ways of reading the same underlying structure. When the conjecture first appeared, the reaction from the wider community was cautious. Beautiful, certainly. Provocative, without question. But conjectures in physics are abundant, and elegance alone is not evidence. What matters is whether a conjecture can deliver concrete predictions, whether the conjecture can generate specific numbers that distinguish a genuine insight from a well-crafted guess. And in 2013, the wormhole correlation conjecture could not deliver. The conjecture pointed in a direction. The conjecture could not produce the destination. And in physics, a direction without a destination is not enough. Directions are cheap. Destinations are rare. What the field needed was a calculation, a specific number emerging from a specific derivation, confirming the conjecture's core prediction. That number did not come. For 6 years, that gap between vision and proof stayed open. Physicists explored the conjecture, published papers analyzing the implications, ran thought experiments testing the consistency. But the single number that would have given the wormhole correlation link real teeth, the page curve derived from a gravitational calculation, remained out of reach. The conjecture floated above the paradox, beautiful and suggestive, unable to land. Then the island formula changed that equation entirely. Because the replica wormholes, the ones that produced a page curve, are precisely the kind of connection the Maldacena Susskind conjecture predicts. Passages linking copies of a system, generating physical results through the correlation structure of the underlying state. Before 2019, the conjecture was a vision without concrete backing. After 2019, the conjecture had a specific, verified calculation supporting the claim. A calculation that produces a measurable number confirmed by multiple independent groups. Proving the equivalence between wormholes and correlations formally requires a level of rigor that the field has not yet achieved. But the island formula provided, for the first time, a concrete instance where the predicted link between curvature and correlation generates a verifiable result. For the first time, the vision could point to a number and say, the prediction works here. And the implications, if the connection between curvature and correlation holds in general, are staggering. Consider what the combined results point toward when placed side by side. The island formula shows that information trapped inside a black hole behind the event horizon is already accessible from outside, connected through correlations encoded in a surface deep within the bulk. Replica wormholes show the connections between abstract copies of a system, connections with no classical equivalent in the physical world, produce the dominant contribution to the entropy of radiation. And the Mauldasena-Susskind conjecture proposes, at the deepest level, that those connections and that curvature are one and the same phenomenon, not two separate processes that happen to produce the same answer. One phenomenon wearing two masks. If all three results are converging on the same conclusion, and the page curve derivation provides strong evidence that they are, then a picture begins to crystallize. A picture that challenges the most basic assumption humans carry about how reality is organized. Start with the boundary. The entire history of the paradox rested on one assumption. The event horizon is an absolute dividing line, a surface that permanently separates two domains with no channel between them. Every framework, from Hawking's original calculation through complementarity and firewalls, accepted that assumption without question. But the island formula says the assumption is wrong. What counts as inside and what counts as outside depends not on where a surface sits, but on how correlations are distributed across the underlying state. Early in the black hole's life, the horizon marks a genuine separation. After the page time, when the island surface takes over, the boundary shifts. Information that appeared to be trapped behind the horizon is already, in the deeper description, part of the external radiation. The boundary between inside and outside, according to the island formula, is not a wall. The boundary is a pattern of correlations, an informational distinction, not a spatial one. Follow the logic one step further, and the ground shifts beneath your feet. If the boundary between regions depends on correlation rather than position, then the concept of position loses a foundational status that physicists had never questioned. Distance, the most basic property separating one point from another, may not be a primary feature of reality. Distance may be derived, emerging from the pattern of shared correlations between regions. Two regions that share enormous amounts of connection would appear, in the emergent description, close together. Two regions sharing almost no connection would appear far apart. Proximity would not cause correlation. Correlation would create proximity. Think about what that means for the gaps between galaxies, between stars, between atoms. Every separation, from the distance between two electrons in a molecule to the gulf between galaxy clusters, would be a consequence of correlation patterns in the deeper state, not the other way around. Consider the night sky. Billions of light years of apparent emptiness stretch between clusters of galaxies. That emptiness looks absolute, permanent. A void so vast that light itself takes billions of years to cross. But if the fabric of the cosmos is emergent, then that void is not a fixed feature of reality. That void is a measure, a direct reflection of how few threads of correlation connect those distant clusters. Darkness stretching between galaxies is not the absence of matter in a pre-existing volume. Every gap is a thinning of the web. The shape of the universe, under this proposal, is not a fixed backdrop painted before the first particle appeared. The shape is a living structure, built from connections, sustained by connections, changing as connections change. Under that picture, the cosmos is not a pre-existing stage. The cosmos is not a container in which events happen. The cosmos is a structure that emerges from information, woven from threads of correlation, the way temperature emerges from the collective motion of molecules. That analogy makes the idea concrete. Temperature is real, measurable with extraordinary precision, consequential enough to build civilizations on. But temperature is not fundamental. No single molecule possesses a temperature. Temperature is a collected pattern arising when billions of molecules move in coordinated ways. Now imagine the same logic applied to distance. Two galaxies separated by 1 billion light-years of apparent emptiness. The separation feels absolute, permanent. But if the fabric of the cosmos is emergent, That billion light-year gulf is not a brute fact carved into reality. The gulf is a reflection of how many threads connect one region to the other. Change the connections, and the separation changes with the connections. That is not a metaphor. That is what the mathematics of the island formula, combined with the holographic principle, suggests. And holography, Maldaceni's equivalence between gravity in the interior and the boundary theory, has been pointing toward exactly that conclusion for over 2 decades. For years, the equivalence seemed like a mathematical convenience, a clever reformulation making certain problems easier to solve. Physicists used the dictionary to translate hard gravitational calculations into easier ones, the way a builder might use metric and imperial interchangeably, without concluding that inches and centimeters reveal a profound truth about measurement. That assessment turned out to be wrong. The island formula demonstrated that the holographic equivalence does physical work. Entropy of Hawking radiation, a quantity that the entire field struggled over for 50 years, emerges cleanly from the interplay between bulk curvature and the boundary theory. What physicists once treated as a convenience for theorists turns out to be a window, a genuine opening into how physical reality is organized at the deepest level anyone has reached. And here is the pattern that crystallizes once every result is placed alongside every other result. Holography says the interior of a region can be encoded entirely on the boundary. What about information trapped inside a black hole? Already accessible from outside, says the island formula. The Maldacena Susskind conjecture says bridges and correlations are the same physical phenomenon. Replica wormholes say that connections between abstract copies of a system, copies with no physical location, produce measurable physical results. 4 independent lines of evidence, developed across 3 decades by hundreds of researchers working on 4 continents, all converge on one implication: separation between 2 points. The most fundamental feature of the cosmos may emerge from correlation. The fabric may not be a stage. The fabric may be a web. And the 50-year fight over information, the bitter argument about whether black holes destroy records, may have been the first hard evidence pointing toward that conclusion. Not because the fight was designed to reveal how the cosmos is built, but because the tools needed to resolve the fight applied fully could not help but reveal the structure. The answer to a narrow question about preservation turned out to require, as a precondition, a glimpse of a far larger architecture. Now, step back. Zoom out to the full arc of the 50-year saga, seen from the vantage of that emerging picture. In 1974, Hawking showed that black holes radiate. The radiation appeared to carry no trace of what fell in, no fingerprint, no signature of any kind. For decades, the physics community treated the problem as a question about preservation. Do the records survive, or are the records permanently erased? 2 frameworks in direct contradiction, with the fate of all information in the cosmos hanging in the balance. But the instruments that resolved the contradiction have revealed a deeper truth about the framing. 50 years of struggle were never only about records. That struggle was the first serious window into a structure that nobody suspected even existed. And that changes how the entire 50-year saga should be understood. The conventional narrative says Hawking posed a problem. Physicists struggled for decades, and eventually 2 groups solved the problem. Under the conventional narrative, the story ends with the page curve. But the conventional narrative is wrong. The story does not end with the page curve. The page curve is the beginning of a larger story, a story about the architecture of reality. Walk through the sequence one final time and notice where each step was actually leading. Hawking exposed the contradiction. Complementarity tried to hide the contradiction behind a boundary, and the attempt failed. The firewall argument then proved that every comfortable exit was sealed. The Maldacena Susskind conjecture proposed a deep link between curvature and correlation, but the proposal could not produce the decisive number. And then 2 groups, wielding tools from a separate shelf, produced the number on a single day. The mechanism behind the number, the replica wormholes threaded through the gravitational path integral, works precisely because curvature and correlation are 2 faces of one structure. Every single step in the saga forced physicists, whether willingly or not, to apply information tools to gravitational problems. Every step chipped away at the wall, the supposed barrier between the particle world and the gravitational world, revealing the wall to be thinner than anyone believed. And the final resolution works because that wall does not exist at all. Both pillars of physics were never adversaries. 50 years of fighting made the pillars appear to be enemies, because the tools available in the 1970s, limited as those tools were, could only capture one face of a deeper structure at a time. Both faces belonged to the same underlying object. For decades, two communities of physicists worked in parallel, each convinced the other was studying a completely separate domain of nature. One group described particles, forces, and the invisible bonds tying distant systems together across vast distances. The other group described curvature, horizons, and the large-scale shape of the expanding universe. Both communities spoke with confidence. Both produced results of extraordinary precision. And both were describing the same reality from opposite vantage points in vocabularies that obscured the shared subject. Imagine two cartographers mapping the same continent from opposite shores. One draws rivers, forests, and mountain passes measured by the journey on foot. The other draws coastlines, ocean depths, and tidal patterns measured by the view from the sea. For decades, each cartographer insists the map captures a different territory. Then one expedition forced across from shore to interior discovers the two maps overlaid perfectly. Every river mouth matches a tidal channel. Every mountain pass aligns with a coastal ridge, and every valley corresponds to a contour in the depth chart. Those maps were never competing. Both were always two projections of one continent, drawn in incompatible notation. The paradox forced exactly that crossing. The event horizon of a black hole is the one place where both vocabularies collide, and the confrontation at that boundary revealed the translation key. Correlations are curvature, and curvature is correlation. The two languages were always dialects of a single tongue. And the information paradox, by forcing physicists to examine the exact place where both faces meet, became the first serious crack in a wall separating those two dialects, a wall that was always, from the beginning, an artifact of limited perspective rather than a feature of nature. Records survive. That was the original question, but the mechanism preserving those records has revealed unmistakably that the original question was always a window into a far larger structure. The island formula and the replica wormholes behind the formula have opened a question that dwarfs the original paradox, a question about the nature of distance, of separation, of the architecture holding the cosmos together. Because if correlations and curvature are two aspects of one underlying structure, then the fabric of the cosmos may not be a fundamental feature of reality. The fabric may be emergent, woven from threads of connection, held together by the same correlations that preserve information across a black hole's event horizon. A paradox that began as a narrow contradiction about one exotic object, a dying black hole radiating into emptiness, has opened a window into the deepest question physicists have ever confronted. What is the cosmos made of? And that question remains genuinely open. Not open in the sense that nobody is working on the problem. Hundreds of researchers are pursuing the problem at this moment, across dozens of institutions, publishing results at a pace that would have been extraordinary a decade ago. Open in the sense that the answer has not arrived yet. The tools are new, barely a few years old. The territory is vast, far larger than the original paradox that opened the territory. And the map, the full map of how correlations weave curvature, is still being drawn. The island formula has been derived in simplified models. In the controlled setting of anti-de Sitter space, a theoretical arena with a negative energy density and a convenient boundary at infinity. The actual universe has a positive energy density, a cosmos that expands faster every second, with no convenient boundary. Extending the island formula from that controlled arena to the full complexity of the observable cosmos is not a minor technical step. The extension is a frontier in the truest sense. A door that opened in 2019, leading into territory where no physicist has walked before. Partial results are encouraging. and multiple independent groups across 4 continents are pushing deeper every month. And the prize waiting at the end of that road is extraordinary. A formula that describes how information behaves in the actual cosmos, not a theoretical proxy, but the specific universe where stars burn and galaxies collide. The observer problem opens an equally breathtaking door. The island formula explains the entropy of radiation with precision that exceeds any previous approach. But the formula says nothing about falling through the event horizon. What does a person, an actual physical observer dropping toward a black hole, encounter at the crossing? Complementarity originally predicted a smooth passage with no unusual effects. The firewall argument predicted a wall of lethal energy at the crossing, instant destruction for any object making the attempt. The island formula sidesteps the question entirely, calculating entropy from outside and offering no comment on the interior experience. Nobody knows what happens at the crossing. The answer is not hidden behind a paywall or buried in a classified archive. The answer does not exist yet. No formalism currently available can describe what an observer would experience, moment by moment, while moving through a region where the fabric of reality steadily transitions from one description to another. Answering that question would reveal a profound truth about the relationship between curvature and experience. What does the fabric of the cosmos feel like from the inside when the fabric is being torn apart? A third frontier sounds like science fiction, but sits squarely within reach of the new tools. Can the preserved records actually be decoded? 50 years of struggle established that records survive. The page curve proves the records are encoded in the radiation, and the island formula demonstrates that the records exist in correlations, in relationships between particles scattered across enormous volumes of the cosmos. But nobody has built the decoder. Building one would require processing correlations between particles separated by billions of light years, a feat beyond any technology any civilization has approached. And yet the theoretical framework guaranteeing the records exist also guarantees, in principle, that a sufficiently advanced decoder is possible. The instruction manual has not been written. The door to writing the manual is open, and the implications of walking through are staggering. Even the deepest conjecture at the center of all these results, the proposal that correlations and curvature are the same physical phenomenon, remains unproven in the strict sense, consistent with every known result, supported by the island formula, by replica wormholes, by holography, and by decades of converging evidence from the study of gravitation at the smallest scales. But consistent support is not formal proof. The conjecture has not been established from first principles, not in the rigorous way that the page curve was established. No independent experiment has confirmed the conjecture directly. And until that confirmation arrives, the proposal remains a conjecture, the most compelling conjecture in modern physics, but a conjecture all the same. Consider what proving the conjecture would mean. Every branch of physics, from particle interactions to cosmological expansion, rests on the assumption that distance between objects is a bedrock property of the universe. Remove that assumption, and the frameworks describing all of physics, from nuclear forces to the expansion rate of the cosmos, would need rebuilding from the ground up. Not because those frameworks are wrong. The frameworks would still produce accurate predictions, the way Newtonian mechanics still sends spacecraft to Jupiter. But the foundations beneath those frameworks would shift, the same way Einstein's curved space-time shifted the foundations beneath Newton without invalidating the predictions. Proving the conjecture would not merely close a chapter in the history of theoretical physics. Proving the conjecture would rewrite the opening sentence of the entire discipline. Distance is not fundamental. And that single sentence, confirmed, would be the deepest revision to the foundations of physics, the most profound rewriting since Einstein replaced absolute time with relative time in 1905. So the 50-year fight opened more doors than the fight closed. And that is not a failure. The original question has been answered. Every collision, every crossing of every horizon, every fraction of information that has ever existed is preserved in the correlation structure of the cosmos, the mathematics confirming that survival is verified, clean, and undisputed within the simplified models where the derivation has been completed. But the answer opened a frontier, and that pattern is the signature of a genuine revolution. When a problem that consumed 50 years yields to a solution, and the solution reveals that the original problem was always a small window, a narrow crack into a much larger structure, the result is not closure. The result is a frontier, wider than the question that opened the frontier, and deeper than anyone imagined when the fight began. More strange and more beautiful than the contradiction that started the whole endeavor. The two theories that appeared to be enemies for 5 decades were, all along, two languages for one reality. The apparent conflict arose from applying each framework in isolation, when the true answer required both applied together in the complete way that Pennington and the Aumharry group finally demonstrated on the same day in May of 2019. And the 50-year saga, with every dead end and broken framework and shattered consensus, was the long, painful process through which an entire scientific community assembled the evidence for a deeper unity, piece by piece, across 2 full generations of researchers. But the mechanism preserving those records points, unmistakably, toward a picture of reality that nobody expected. Nobody anticipated the picture, not back when a young physicist in Cambridge calculated, for the first time, the glow of a dying black hole. Nobody anticipated the picture when complementarity promised a comfortable escape, or when firewalls sealed every remaining exit. A picture in which distance is not the background. Distance is the emergent pattern. Separation is not a given property of the cosmos. Separation is a measure of shared information. And the universe, at the deepest level anyone has been able to reach, may be a web of invisible threads, each thread a correlation, each correlation holding a piece of the fabric together. The same fabric that the 50-year fight has only begun to pull apart and examine. The fight was never about whether the universe remembers. The fight was the first glimpse of what the universe is. And so the first glimpse widens into a view. Each atom carries a record. Every collision, every exchange of energy, written permanently into the fabric of physics. That was the promise at the beginning. A promise that one calculation threatened to shatter. A promise that 50 years of crisis tested from every angle. The records survive. 2 researchers, working on opposite coasts, confirmed the survival on the same day, using tools that had been sitting on the shelf for over a decade. Permanent erasure threatened in the first act, a comfortable framework betrayed in the second, and in the third, rescue from tools nobody thought to pick up, and in the fourth, the revelation that the crisis was never about the original question. Every chapter in that 50-year saga pointed toward a single conclusion. 2 theories that appeared to be adversaries were never fighting each other. Both were speaking different languages about the same structure. The universe remembers. Records are preserved, at least within the simplified models where the derivation has been completed, encoded in correlations between particles scattered across vast distances. And the mechanism preserving those records was not exotic, not new. Existing physics, applied completely for the first time, produced the answer that half a century of partial applications had missed. No gap in human knowledge caused the 50-year crisis. An incomplete application of knowledge that already existed caused the crisis. Every dead end, every shattered consensus, every framework built and then broken was a consequence of applying one half of reality at a time, when the answer required both halves together. Thoroughness delivered the answer. Patient, complete application of tools that were available all along. And here is what thoroughness revealed. A crisis that began as a contradiction between 2 theories over decades turned out to be a crack in a wall that nobody knew existed. On one side, quantum mechanics. On the other, gravity. Physicists were forced to look through that crack, and what lay beyond was not 2 separate domains. A single structure waited on the other side. The fabric of space and the invisible connections between particles may be the same phenomenon, woven from the same quantum threads. 2 pillars of physics were never adversaries. Both are descriptions of one deeper reality. 50 years of struggle have only begun, slowly, to map the territory that the crack exposed. An observer looks up at the night sky and sees galaxies separated by enormous gulfs of darkness, empty space stretching in every direction. But the darkness is not empty. Every point is held in place by invisible threads. The same threads the crisis revealed. Space is not the stage. Space is the web. The real question was never whether black holes destroy information. The math keeps pointing toward a deeper puzzle, one stranger and bigger than the original crisis ever suggested. 50 years of crisis did not end with a final answer. 50 years of crisis revealed a crack in the wall between two theories that turned out to be one. I hope you found some value in the deep dive today. If you did, and you want to support the research that goes into these videos, hitting that like and subscribe button goes a long way. Your support allows me to keep digging deeper into the questions that matter, and to keep bringing you the physics that challenges how we see the universe. I will catch you in the next one. Let curiosity guide you, keep learning, and know that you are always appreciated.